All right, ladies and gentlemen, good morning again, and welcome to episode 7 of Fighting for A5, where we go over the document, problem number 7. I received a lot of questions regarding this problem, basically asking, how should you show your work? Are we allowed to, do we have to define our random variable? But also, a lot of you asked me about calculator notation. And I've been very clear throughout the year about not using calculator notation. So I just want to say that you should not use calculator notation. And even though the scoring guideline sort of showed you calculator notation, this is an old problem. I think it's from 2006. Scoring guideline, or maybe 2009. Anyway, it's an older problem. And scoring guidelines have become a little bit more strict in recent times. And frankly, I agree that calculator notation really does not show an understanding of proper statistical notation. And so I want to say again, please do not use calculator notation. Learn the proper practical statistical notation. If you write a research paper and you say, and somewhere in your research paper you write binomial CDF, blah 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 blah, people aren't going to understand what that means. Okay, so learn the notation. So once again, the question is, are you allowed to use calculator notation? The answer is all right. So I don't know how that came out. We'll see in post-production, but hopefully you heard that. It was a clip from a song, and it repeated the word no over and over again. All right, anyway, let's get into this problem. So these types of problems are so nice because they're all the same. Yeah, different numbers. Maybe you might be finding probabilities of different types of contexts, but you're given a distribution, and then you're asked to find the probability using information from that distribution. And then later on, you take a sample from that distribution and find the probability of that. So these are all very similar in structure. Now, if you don't understand how to calculate these probabilities, or if you don't understand these structures, then yes, you have a problem. But hopefully at this point, we've seen so many of these that you're starting to really have a good grasp of these problems. Anyway, let's get into it finally. So what is the 70th percentile of the distribution of stopping distances? Well, we are told that tests show that the new tread pattern enables the cars to stop completely in an average distance of 125 feet with a standard deviation of 6.5 feet. And the stopping distances were approximately normal. Wow, how nice for us. So for starters, I'm going to go ahead and define a random variable. And I'm going to say let x represent stopping distance. Right, this is the variable being measured, stopping distance in feet. And this is for just any random car, all right? We're told that these stopping distances are distributed normally with a mean of 125 feet and a standard deviation of 6.5 feet. And by the way, I just actually want to backtrack. The stopping distances are for cars with this particular tread of tire. But I think if you just define X to be stopping distance, you'll be okay. Now, we're looking for the 70th percentile of this random variable, right? So, I mean, the idea is we have a distribution of the population. Okay, these are all the possible X's. So this is your distribution of X. We're told that it's approximately normal. We know that on average, the cars will stop at 125 feet. But of course, there will be some cars that stop below that, some cars that stop above that. What we want is the 70th percentile. We're looking for, and the notation would be X subscript 70%. We're looking for the car whose stopping distance is greater than 70% of all other stopping distances. All right. And so this is going to rely on the relationship that says Z is equal to observed minus mean over standard deviation. This is an extremely important relationship, and it helps us solve problems like these. So the equation that you'd set up is to find this, you'd say Z of 70%, right? Because we want, in order to obtain this value here, we need the Z-score of the 70th percentile. And that's going to equal X of 70% minus mean, which is 125, over standard deviation, which is 6.5. Now, Z of 70%, you will use inverse norm on your calculator, type in 0.7, the mean will be 0 and the standard deviation will be 1. That's the standard normal model. So when you see the letter Z, Z is referring to the standard normal model. Z is a distribution that is normal with a mean of 0 and a standard deviation of 1. All right. And that's true. So any normal distribution that we have can be converted into the standard normal model by subtracting the mean from each value and dividing each value by the standard deviation. So anyway, we use inverse norm to get our z-score. 0.5244 is equal to the unknown value okay? And from here is where you get sort of the expression that a lot of you saw in the scoring guideline, which is that the value you're looking for will equal 125 plus 0.5244 times 6.5. And that, of course, ends up being, let me just quickly type this into my calculator. $128.4086 feet. And this is your 70th percentile. All right, so I maybe went ahead and showed more steps than are necessary, but I'm gonna highlight now what I definitely think you should show. Define your random variable, define your distribution. It wouldn't be a bad idea to show this equation, and then you can go ahead and show your final answer, of course, in context. So that means with units. All right, part B. So now we're diving in to this population, and it looks like we're randomly selecting 5 cars. And we want to know, what is the probability that at least 2 of 5 randomly selected cars in the study will stop at a distance that is greater than the distance calculated in part A? This is a sneaky way of basically asking you to calculate the probability of at least 2 successes in 5 trials. In other words, this is a binomial distribution. So I'm going to define another random variable, let's say y, and I'm going to say that y represents the number of cars that stop at 128.4086 feet or greater, right? Is that what it is? Yeah. No. Stop at, actually, the number of cars that stop at greater than 128.4086 feet. Well, let's, and of course, since we're counting the number of successes in 5 trials, since we're counting the number of successes out of 5 cars, we want to say that y is going to be distributed binomially with 5 independent trials, and with the probability of success being p. Well, what's the probability of success here? Or in other words, what's the probability that any individual car stops at greater than 128.4086 feet? Well, going back to part A, this value that we found is the 70th percentile. What does that mean? Well, that means 70% of the values are below it, which in turn means 30% of the values are above it. So the probability of success is going to be 0.3. Boom. And there you have it. This is the distribution that we're working with, and we're simply looking for the probability. Okay, here we go. P notation, completely required. We're looking for the probability that at least 2 cars out of the 5 stop at a distance greater than 128.4086 feet. So in other words, we're looking for the probability that y is greater than or equal to 2. Now, you can calculate this by hand, or you can use the binomial CDF function on your calculator. The thing is, the binomial CDF function only does less than or equal to, so you will have to convert this into an expression that uses that knowledge. And so we can write this as 1 minus the probability that y is less than or equal to 1. Right? So just to give you a sense of what this distribution of y might look like, think about the possible outcomes of y. So we're counting the number of cars that stop at a greater than a distance than 128.4. So out of 5 cars, you could have 0 that stop at a greater distance. You could have 1, you could have 2, blah, 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 all the way up through 5. So the only possible outcomes for y are 0, 1, 2, 3, 4, and 5. This is a discrete random variable, okay? Each one of these outcomes has its own probability. I'm not going to go ahead and calculate the actual probabilities, but I think it's, let's see. I would imagine it kind of looks something like this. Something along these lines. All right. So why is it enough to say that the probability that y is greater than or equal to 2, why is that equal to 1 minus the probability of y being less than or equal to 1? Well, I'm going to color in the bars that represent y greater than or equal to 2. So that's this bar, this bar, this bar, and this bar. So it's taking into account y is equal to 2, 3, 4, or 5. Now, in total, if we take into account the sum of the probability of all the outcomes, the total probability is 1. Okay? So that's where this 1 comes from. So I'm taking the total probability and I'm carving out what I don't want to count. And that is, I'm carving out these green bars. All right? So in total, we have 1. We're subtracting out the green. And what will we be left with? We'll be left with the red. All right, so that's what we want to do here. And so it turns out that this probability, so the probability that y is greater than or equal to 2 is equal to, I'm going to use my calculator real quick. Second distribution, I go to binomial CDF. Yes, I'm using these distributions, but I am not, I'm not writing them down. I'm writing proper statistical notation down. So if I remember correctly, the inputs are is a value, and then n, and then p. Oop, wrong. So we're gonna, the inputs for binomial CDF are gonna be the number of trials, comma, the probability of success, comma, and then the upper bound, basically, of what we're trying to find, which in this case would be 1. So we have 1 minus 0.5282, and that, of course, is 0.4718. And that's the probability that y is greater than or equal to 2. Now, again, I wrote a lot more than is required, so I'm going to highlight what I want to see in your work and what the AP will want to see in your work. So I'm going to highlight in orange since I already have some yellow highlighter going on. But you're definitely going to want to define your random variable and do it appropriately. In other words, since we're counting the number of successes in a fixed number of trials, be sure to list those fixed number of trials, which in this case is 5. Define your distribution, and then your p notation. So really, you don't have to go through the steps of showing 1 minus blah, blah, blah. I just want to make sure that you understand that that's how you're going to have to calculate these numbers. All right, cool. Part C now. What is the probability that a randomly selected sample, here we go, folks, sample, implying sampling distribution, sample of 5 cars in the study will have a mean stopping distance of at least 130 feet. So now what we're interested in is the sampling distribution of sample means. This means, no pun intended, that we have to define a new random variable. And since we're looking for mean stopping distance, and since I already have a random variable of x, which is just stopping distance, I'm going to use x bar. So x bar is going to be the mean stopping distance in a sample of 5 cars. And now, how is x bar distributed? Well, since the population is normal and since this is a random selection, the central limit theorem will apply. And so that means the center of the sampling distribution is going to equal the center of the original population, which is 125. And the standard error of the sampling distribution will equal the population standard deviation divided by radical n. So that would be 6.5 divided by radical 5. All right, you might be wondering, why are we using the normal distribution instead of the t-distribution? The key here is we are given all the population information. We're not inferring anything about the population. We know it all already. We're using the known information about the population to gather something about samples. So the fact that we're not inferring anything and the fact that we have all the population information means that we are allowed to use the normal model. If we don't know population mean and don't know population standard deviation, then we're forced to use the t-distribution, okay? If you have more questions on that, watch the t-distribution videos. All right, so what are we looking for? So we have our definition of our random variable, we have its distribution, and now all that's left is your p notation statement, and we're looking for the probability that x bar is greater than 130. This is quite simply a normal CDF problem. Um, 6.5 divided by radical 5 is, so let me just write this, that this is 2.9069. So normal CDF, 130, comma 99999, comma 125, comma 2.9069. So this probability is about 0.0427. Another question that came up was, hey, they're using the z distribution. In other words, they wrote their probability in terms of z. That's totally fine. You can use z, you can use x bar, as long as your distribution and the random variable is defined. I don't care which one you use. They're equivalent. So in other words, you could have made the statement that you're looking for the probability that z is equal to 130 minus 125 over 2.9069. So that's the transformation from x bar to z, right? Just to sort of really make sure you understand that these two are exactly the same thing. We know, let's see, if I take an x bar and I subtract the mean, which is 125, and divide by the standard deviation, which is 2.9069, what is that equal to? Where have we seen that before? Some value, some observed value minus the mean over the standard deviation. What is this equal to? Let's go up here. Take a look. That is exactly equal to z, right? And so when we transform x bar by subtracting the mean and dividing by the standard deviation, we get z. And as long as we do the same thing to the numerical value, we have probabilities that are completely identical. All right. Now, what work do you need to show? You need to show this. You need to show this. This is good too. And then a probability statement. And I don't care which one you use z, use x bar, whatever is fine. All right, folks, that is all. I hope you enjoyed the videos. Take care, have a good night. And I'll be back again. Well, I'm not gonna make another video tomorrow because there's nothing else to make a video for, but I'll assign another assignment tomorrow. So anyway, we'll talk then. Take care, bye.